Attendance sheet is going around. And we are picking up where we left off last time. Okay, talking about linear differential equations with constant coefficients, okay, which represent, as I said, about 90% of all differential equations that you will solve by hand as an engineering student. Okay, and so we get this out of the way right now. So anybody need a copy of the recipe? Recipe distributed last time. Step by step, how do you solve a differential equation? Everybody got it? Should have the recipe out, right? Remember I said moving forward, we are not going to do any steps to this until we've got somebody from the peanut gallery helping me out, okay? To make sure you guys are with me. No one needs a copy. You do. Okay, very good. Anybody else need a copy? All right, great. All right, so I believe I've got where we left off last time, which was we talked about the leaking bucket, right? And the idea that we've got volume flow coming in, volume flow going out. The height's going to change. Multiply the height by the cross-sectional area. That means the volume's going to change, all right? And we found out that the height as a function of time has to satisfy this, all right? And it's got the height, the unknown function. It's got the derivative of the height. Any equation that's got an unknown function and one or more of its derivatives is a differential equation. Okay? In addition, these terms are just a linear combination. In other words, I got one term with a derivative. I'm adding it to another term with a function. I don't have a square root in here. I don't have a sinusoid. These a's and these k's. A is the cross-sectional area, all right? K, proportionality constant here, it depends on what kind of valve I've got. It depends on what kind of fluid is in here. Is it molasses or is it water, that kind of thing. So that means the A and the K are just parameters that are constants. So what we've got is a differential equation that's linear, right? No square roots, no h multiplied by derivatives, nothing like that. Okay, and constant coefficients. So first order linear DEQ, differential equation with constant coefficients, and that means that the recipe does in fact apply. Okay, and last time I believe we got through step one of the recipe. So without working the whole step, if you recall, we did this guy, step one, the transient solution. Okay, and the transient solution was of the form e to the st. Okay, and I think we came up with this guy, h transient of t. All right, so this is just the transient part of the total solution. I believe we got c1 e to the minus k over a times time. So I got the problem parameters in there, k and a, part of the solution. Questions on where we left off with the transient part? This is where you guys help me do the rest. Okay? So after I'm done the transient solution, according to the recipe, what is the next step in solving a differential equation? Steady state. Who said that? All right, steady state. So again, we're doing where you can answer one question today. Okay? That's it. Then I need somebody else. So run with it. So a steady state solution. Okay, that's what I want to do. Can you tell me a starting point for how I'm going to go about doing that? Feel free to refer to the sheet, right? Figure this out. You're still up if you want it, right? This is still you. Steady state means what am I trying to do here? Okay, so he said assume a form of the solution based on what? The input. So what's the input to this problem? Is this it? Is this the input, the k? Is time the input? All right, so just to be clear about this, mathematically, the input is whatever is on the right-hand side of the equation. Physically, the input is what you're actually doing to cause something to happen. Okay, so what am I actually doing here? I'm adding water. Okay, but actually, I didn't say what that was, right? Did I just turn on the faucet? In that case, Qn would be what kind of function? That'd be a constant. I already got the homework going. I'll post that shortly. I've got a Qn that corresponds to this, right? Back and forth in a sinusoidal way. You can do that. So we really actually have to say what that is. So we need to know what the forcing function is. So let's suppose I'm just turning on the faucet. So Qn is equal to a constant. We could put a number in here, but let me put a parameter that could be any number. So I could just leave it as Qn, but Qn is a general term for any forcing function Q. So I'm going to call this one the letter B. Okay? The letter B is a constant value. So this would correspond physically to turning on the faucet a certain amount, right? And, we'll make it clear here, this problem will be a constant value. Qn is equal to B, whatever. Volume flow rate, meters cubed per second. Okay? So, this is what my forcing function is, right? This is my f of t on the recipe, okay? The right-hand side, f of t. So if the forcing function is a constant, okay, I've got choices on the recipe here. What kind of result am I going to get for the steady state solution if the input's a constant? I'm going to get another constant. All right, and again, now part of this is just experience, okay, but it's inductive kind of logic, right? I mean, it's look at this. I'm going to take a function, I'm going to take its derivatives and add it to itself and get a constant over here, right? And so how am I going to be able to do that and get like terms, right? If this thing, if the function is going to be added to itself, you could say, well, the derivative would be a constant if I used like a linear function, okay? But then when I add it to itself, I'd get a linear term, right? I'd get a t. So if the right-hand side over here doesn't have any t's in it, and it's just a constant, then I'm going to have constants over here. Okay, it's the only way I'm going to be able to add up terms and get a constant. All right, so this is the idea behind it. So according to the recipe, right, if I had, like on your homework assignment for this problem, all right, you're going to have like a sinusoidal function. If the right-hand side is sinusoidal, then I can't add up quadratic equations and constants and get a sinusoid. Right? If I got a sinusoid here, I got to have a sinusoid for a steady state answer. So it's basically, the approach to solving this, it's an engineering approach. It's just there's no theorem or, proof behind it. It's just pragmatism. Look at the equation. What's the possibility? Okay, and that's it. And you plug it in and find out what it has to be. Okay, so great. So procedurally, I want to do what now? If the forcing function's a constant, I'll do what? What does it say on the sheet? Okay, so assume a steady state solution that is also a constant, right? Do you know what constant the steady state solution is yet? All right, so if you're going to assume that it's a constant, just make it an unknown letter, right? An undetermined coefficient. That's what we're doing here, the method of undetermined coefficients. So because this is a constant, we will assume, okay, that h steady state of t is equal to some constant. Now, if I'm going to use a constant for this, I probably don't want to use any of the letters that I already have here. Okay, so this is something to think about notation-wise. We've got a table here that just suggests what you should assume. Okay, so I've got things like a constant a. Should I use a constant a as the assumption here? No, because that one's already taken. Okay, so again, don't just blindly follow the sheet. I mean, it's the spirit of the sheet. So I can pick whatever letter I want. So I'll use capital E. Okay, h steady state is equal to capital E, and we're going to call that then a constant. All right, so if my Qn is B, my original equation is a dh dt right, plus k times h of t is equal to qn. You know, that's the b. So that's the specific equation we're trying to solve now. So if I assume that the answer is of the form E, how do I figure out what E should be? Right, because right now, E is undetermined, right? We don't know what it is yet. We're just saying, hey, this is an undetermined value that we're going to have to find. Yeah, so you take the assumed steady state solution and you see what does E have to be in order to satisfy that equation. That's it, right? There's no other way to figure it out except plug it in. Okay, so I'm going to now plug in. I'm going to plug in h steady state of t is equal to E, right? As a function of time, it's just a constant value. Okay, there is no t. So I need a times the derivative of this. So I'll write it out. A times the derivative of the constant E. Okay. Plus, I've got k times h. Well, the steady state solution is just E, right? And that is supposed to be equal to B. So literally, you just plug in the assumed solution and see what it has to come out to be. So how about the first term? What's the derivative with respect to time of a constant? 0. Okay, so this entire term right here is 0. All right, the constant does not change in time. Okay, and so what you're getting here is essentially k times E is equal to B. Ke equals B. What am I trying to solve for here? E. Okay, so according to this, E has to be what? Yeah, B over K. So the assumed solution was some constant E. I just figured out what E had to be. E has to be B over K. Okay, and so the conclusion is that I've got the answer for the steady state. H steady state, right, is equal to E, which is B divided by K. And at this point, you got a problem with a bunch of letters in it. Be thinking about, you know, what are these letters? What's B? That's the Q in, the volume flow rate coming in. What's K? It's got to do with the out, right? I heard out. It's got to do with the valve and the liquid. So again, think about the physics, right? So just look at the letters. So I just said that a steady state solution for this problem, the steady state value of the height. In other words, how high up does this thing go and sit there, right, when the water coming in is at the same rate as the water going out? That's the steady state. What does it depend on? Well, according to this, it depends on how fast the water's coming in. That makes sense. It depends on how big the valve is at the bottom, right? And whether I got molasses or water. That's the K. These are the things that has to depend on, right? Sanity check. So it makes some sense, yes? Okay. Very good. So what do I have? I've got 2 parts. By the way, each of these parts is worth 5 points on your final exam. Okay? I got a transient solution, C1 e to the minus k over at. I got a steady state solution, b divided by k. I'm not done solving the differential equation yet. I got to go back to the recipe. Steps 1 and 2 seem to be done. What's step 3? Find the total solution. So when I got these 2 parts, how do I get the total? Add them together. Good. All right, so part 3 is the total solution. Okay, and so what is that? Well, I want h of t is equal to the sum, h transient of t plus h steady state of t. Somebody give me a y for that. Why is it that if I have this part, and then I also have that part, Why is the solution the sum of the two as opposed to either or? Right? Like I solve a quadratic equation, I get two answers for x. Okay? The solution's not the sum of those two answers, right? It's either or it's both of those answers. Why am I adding these up?
Because it's the initial conditions.
Talk more about that. You said, what does it have to do with the initial conditions?
Because the transient one is t equals 0.
Okay, so what he's saying is, I'm going to need this part in order to satisfy initial conditions. That's true. Can somebody give me a more mathematical explanation for why is it that the most general solution is the sum of the two of these? So let me back up the question. If I take this, okay, and I plug it into the original equation, do I get B? No. So this part does not satisfy the original equation. What do I get when I plug this part into the left-hand side? I get 0. That's how I found this part. Okay. Now, this part, if I plug this into the original equation, the steady state, do I get B? Hey, we could check, right? Let's plug it in. A times the derivative of B over K. What's the derivative of B over K? 0 plus K times B over K. Do I get B? Yes. I better get B. That's how I found this, right? I found this so I would get B. So what we've got is two solutions. One, that when I plug it in the left side, I get nothing. Two, that when I plug it in the left side, I get B. That second part might make you think you're done. This one satisfies the equation. But if I add that to it, that gives me nothing. Doesn't it still satisfy the equation? Right? So it's a completeness issue. It's not complete unless I add the extra part, right? It's like when I do an indefinite integral. There's an infinite number of these answers. I got a plus c on the end. Okay, now, in addition to satisfying the equation, your comment was, I got to satisfy whatever this is. Initial conditions. What's the situation at t equals 0? It could be a number of things. I could start with water in the tank. I could start with the tank half full. I could start with the tank empty. Right? Any of these could be initial conditions. This guy, B over K, is one value all the time. Does this satisfy initial conditions? You know, only if you start it right at B over K, right? And it just sits there forever. We call that the trivial solution. Nothing happens, right? In other words, if I had the tank filled up to just the right amount, where the Q in equaled the Q out, right? And I pulled the cork out the bottom and turned it on, what would happen? Nothing. The height would just sit there at the same height, okay? That's it. Any other case in between, this would not satisfy the initial conditions. Okay, so physically, the comment about, yeah, I got to have this one for initial conditions, that's true, right? But the point is, adding this to this is the most general solution, right? Because this part here can always be added to the steady state, and it will still satisfy the equation. Right? So if you don't do it, your solution's not complete. And if your solution's not complete, you're probably missing some physics. Okay? You guys with me? All right, so you add the two together. So let's do it. We got the two. Okay, so this means that h of t is equal to, I got c1 e to the minus k divided by a times time, okay, plus I got h steady state, which is b divided by k. So again, whenever you work a problem with all these parameters in it, you want to take an inventory of your letters here and make sure you know what's what. What's the k again? That's the proportion for the output, right? How big's the valve? Is it molasses or water? What's the A? Area of the tank. That's a problem parameter. What's the B? It's the Q in, right? I turned on the faucet. It's coming in at however many cubic meters per second. Okay? So all of these letters are known. What's the C1? It's a coefficient. Do I know what it is? No. Okay, so I'm not done yet. So the point is, at this point, I've got everything figured out except for the constant that pops up in the transient solution. So I'm going to need an equation to solve for that constant. Where am I going to get another equation? Set it equal to 0. So if C1 was 0, then the answer would just be the steady state solution. Okay, and this would be true if we did what I said before, right? If we started the tank right at the height B over K, and we turned it on just right so that whatever came in went out. Okay, and then that would be true. In that case, C1 would be 0. But if I start with the tank empty, C1's probably not 0. Right? Because this is all the time dependence right here, right? The tank's going to fill up. So the C1 depends on what? Initial conditions, right? That's what it depends on. Okay, so again, you can just look at the recipe. In the recipe, what's the last step? Apply the initial conditions. Okay, but my goal of solving all these problems is that we don't have to follow this recipe, right? If we understand the why on every one of these steps, it's obvious what you got to do next. Okay, so I want you to get to that point between now and the final exam, so you're not relying on transcribing this whole recipe down onto your crib sheet. Okay, you want to understand the why so you can just move forward and solve these problems. Okay, all right, so I need an initial condition. So I didn't say what this was, right? So this particular problem, we're kind of walking you through different possibilities for the physics, for the Q in general, at the very beginning of the problem, you will have an equation where you know what the right-hand side is and you know what the initial conditions are. It's part of the problem statement. Okay, so at this point, the question is, what problem are we really solving here? Why don't we try the one when the tank starts empty? Okay, that's the interesting problem, right? Because then I got nothing, and I'm adding the liquid, and we're trying to figure out how high does this thing end up, okay? And how long does it take to get there, right? So, initial condition, let's suppose that the tank is empty, right? So suppose H of 0 equals 0. Okay, so this is the tank is empty, okay, at time t equals 0. That's the idea. So if the tank is empty at t equals 0, the question is, what would be the C1 that would make that true? How can I do that mathematically? What am I going to do with this? All right, plug in 0 for t into this equation, and then set the equation equal to what? 0. Now, this side doesn't have to be 0, right? I could say 3 inches, 3 inches of water, right? If that was true, I'd plug in 0 for t, and I'd put 3 on the other side. Okay, the initial condition's whatever you say it is, but it affects what the constant will be. Okay, so let's try this. So what is h of 0? I plug in 0 for time. So it's going to be C1 e to the minus k divided by a times 0. I'm just going to write it up there. I'm plugging in the 0. Okay? Plus b over k. And when I evaluate h at 0, I should get what? 0, because that's the empty tank. Okay, so now we got an equation with how many unknowns in it? 1. C1's the only thing I don't know, right? All right, what is e to the 0? Okay, so this guy is 1. So the conclusion is that C1 times 1, right, plus B divided by K equals 0. What am I trying to solve for? C1. So C1 would be what? Yeah, negative B divided by K. Okay, that's the answer for C1. So then the total solution is H of T with that, right, plugged in for C1. So H of T is equal to what? Negative B over K, that's the C1, E to the minus K divided by A times time, right, plus B over K. Can I simplify that at all? Yeah, I can take a B over K out, right? This way is actually a little more insightful. If I factor out a B over K, okay, because I got it in both terms, then what would I have? The first term's negative, and this term would be what? 1. So a clean way to write this might be 1 minus, right? Just flip the order of the term. 1 minus this guy, e to the minus k over a times time. This is the solution. All right, so what do we like to do in engineering once we get a solution? Do what? Okay, prove it is one thing. So how would you know if this solution is right or not? How do you know? Let me ask you this. When you solve a quadratic equation, you get two numbers for x or time or whatever. How do you know it's right? I'm sorry, that was too much at once. One person, tell me. Plug it back in, right? Quadratic equation is ax squared plus bx plus c equals 0. When you plug it back in, you should get what? 0. Okay. So I got a solution now, which is not a number. It's a function of time. How do I know if it's correct? I can plug this back in, right? To what? I want to plug it back into the original problem here, right? This is a b, okay? And, you know, so the original problem we're going to plug this back into is this with a b over here. That's the equation. What else does I have to satisfy? The initial condition. So it needs to satisfy h of 0 is 0, and it needs to satisfy, give me a b, right, when I plug it in. So you could probably just about do this in your head. I don't know. Let's do it in our head. What's the derivative of this? Here, we'll just write this as the check. Okay? So what's dh dt? Can we do this? Maybe look at this term, right? This term. What's the derivative of the first term? Is it? What happens to the b over k? Is it 0? The b over k multiplies the exponential function. The constant sits there, right? The derivative of e to the minus k over at is what? The minus k over a comes down. This minus cancels that minus, yes? Okay? The k cancels itself out, right? And then what do I get? I get what? b over a, right? E to the minus k over a times time, like that. Okay, and what about the next term? What's the derivative here? 0. Okay, so I get b over a times e to the minus k over at. Okay, and then what about this one? K times h of t. K times h of t will cancel this, right? So I'll get a minus b right here. right, times plus a b over k. What do you think? Is this going to work? Do you guys want me to work it all the way through? Try to do it in our head here. Okay, so just to be clear, a dh dt, the a will cancel this a, and I'll get b e to the minus k over at, right? Next term plus k times h, the k cancels this. Now I'll get minus b e to the minus k over t, which will wipe out this term. And then I've got plus b over k over here. Here's k times b over k is what? B. All I'm left with is b. What's the right-hand side? B. Okay, so you can write that all out if you want, but the point is it's got to satisfy the governing equation. Okay, and it does. It satisfies the governing equation. What else does it have to satisfy? Initial conditions, which is h of 0 better give me 0, right? Let's double check. What do you get? Yeah, right? At 0, 1 minus 1 is 0. Okay, it had to be the case. I forced it on the C1, right? Right here. That's how we got it. So you always know when you solve a differential equation whether or not you got it right or wrong if you want to take the time. Plug it back in. Okay, if it satisfies the governing equation and it satisfies the initial conditions, then that's it. That's the solution to the problem. Okay? By the way, it's worth noting, okay, if the approach to this kind of bothers you, like if you really like math, okay, and you wish that there was just a theorem or a proof about why this works, right, kind of like the fundamental theorem of calculus, you can prove that, okay? The solution to these differential equations is like it's like an ad hoc kind of engineering problem solving. It's like, let me try and find a function that's going to work and plug it in and see if it works, right? A little bit dissatisfying from a mathematics standpoint, okay, but what the mathematicians have done is they have gone and proved that if you can find a solution, no matter how you find it, if you can find one that satisfies the equation and the initial conditions, okay, then it's unique and it's complete. Okay, so there are mathematical proofs that says, I don't care how you find it, if you can come up with an answer, check those two things, and then that's the only solution, you're done. Okay, so that's great. That's why we like mathematicians as engineers, right? Because they can provide that justification, and then we can figure out how to just get it done. Okay, and that's what this procedure is. It's getting it done. Okay, but once you find an answer, that's all there is. You guys with me? Okay. All right, so here it is. So I said, what do we normally do in engineering when we get an answer? And you said we check it. So we checked it. What else do we like to do? Plot it. Okay, plot it on the final exam. So, man, another problem with a bunch of letters. Dr. K is going to make us plot problems with letters. Absolutely. Okay, why do we like problems that have letters in them? I can use them for whatever I want, right? Any value of Qn, any valve at the bottom, any liquid, molasses, right? Water, doesn't matter. The behavior is still the same. One plot, all those different problems. Okay, that's the reason we like the letters. All right, so let's see if we can do this. How do we plot this thing over time? Okay, we'll probably want to put a number or two, a number in a problem with letters. Okay, but let's see what this looks like. So I'm going to plot over here h as a function of time, and I'm going to plot the time over here. Okay, and so the question is, what do I use for tick marks in a problem like this? Here's the equation we're plotting, right? What kind of tick marks do you think I should use here? For time. Should I go like 1 second, 2 second, 3 second? Should I go like, what do I do? Yeah. Mm-hmm.
Because since you're going to be multiplying it by 1 minus the
All right, so time is never going to go over b over k, or what? Time. Okay, so which tick marks are you talking about? The vertical ones. Okay, so vertical tick marks, I probably want things in terms of b over k, because he's saying, look, well, first of all, at t equals 0, what's the height? All right, so I know it starts at 0. So at some point, I'm going to need some tick marks here. And he's saying, can we have tick marks in terms of b over k? Because when time gets really large, right, t equals whatever, infinity. What's the answer? Yeah, this becomes 0, right? 1, this is e to a negative large exponent. 1 over e to a big number. Okay, so the second term's gone. So look, physically, the answer when t is a large number is b over k. What part of the solution was b over k? It was a steady state solution. What does steady state mean? It means when time is large, what's the answer? Right? So that has to be the case. So this axis over here, yeah, I mean, this needs to be in terms of b over k. So here, this is b over k. All right, so we know the solution's never going to get past this number, b over k. That's a steady state. Great, so we got something on the y-axis. What do I do on the x-axis? T1, T2. So let's think ahead a little bit, okay? Suppose I just, don't use any numbers and I just use like T1, T2, T3. Then if we plot some points on there, what would we get? H of T1, my value would be what? B over k times 1 minus e to the minus k over a T1. Do I want to use that as a data point? Is there any way to get some numbers out of this thing by properly labeling this axis, right, in a way that when I evaluate the function, I can get answers that are like, what do I want to know in time, right? How, after a certain time, how close to the steady state am I? I'd like to get some numbers times b over k. That's what I would like, right? Go ahead. Well, what is the maximum? Okay, so I already solved for that. So what would be the answer? Would it? So he said, figure out what time will give me b over k for the answer. Who knows the answer to that? What is the value of the time that I would get b over k for the answer? Yes, infinity. Right? Because by definition, this is a steady state. This is a decaying exponential. It's never 0. So I got to get t equals infinity before this thing really gets down to 0. Okay, so that's not going to help me. All right, you're barking up the right tree, but it's not going to help me. I know the infinity answer already. It's there. I know the starting point, right? I know the starting point, and I know at infinity I'm up here. How do I get tick marks on here that will enable me to put some numbers on this graph in between 0 and infinity? Say what? Take the derivative. Well, so think about that. So will a local maximum help me out? Does this equation have any local max or minimum? Yeah, I mean, it's an exponential, right? So exponential functions, they do this kind of thing, right? The only place they're flat is out here at infinity, right? All right, that's an exponential decaying that way. You could have an exponential, going up the other way, right? And I get a flat spot out here when t is infinity. But yeah, calculus is not going to help me here. This is really an algebra question. Let me ask you this. I want to know values of h in terms of b over k. My y-axis is b over k, right? Give me a number that I could put for t here so that I can evaluate this on my calculator and get a number.
Time equals a over k.
Sure. What about when t equals a over k? Then this is e to the minus 1, right? What would be another number?
2a
2a over k, 3a over k, 4a over k, right? The time over which this thing transitions to the steady state depends on a over k. Think about it. How big's the tank? How big's the valve at the bottom? This controls the time behavior of the problem, right? And so I want to use values of a over k. Okay, incidentally, that's why we call a over k the time constant, right? Those are the values. It's not, is it t equal to 1 millisecond, 2 millisecond, or 1 second, 2 second, 3 second. It's how many a over k's am I? That's the relevant question. Right? Okay, so, let's take the t values and we can plug in a couple of these things. So one, you said, hey, a over k, what's h of t? Somebody do it for me. When t is a over k, right, isn't it b over k times what? I'll write this one out. B over k times 1 minus, when t is a over k, it's what? E to the minus 1? Give me a decimal. Okay, so this is 0.632 b over k. Now we're getting somewhere. Okay, because now I can put tick marks on here. 0, this is a over k. This is 2a over k, right? And we can go out to whatever we want. Let's do 3a over k, and we'll do a 4a over k right here. Okay, and so after a over k, I'm at 0.632. So I know how far I am, right? I'm 63% of the way up there. So that's roughly maybe here, not quite 2/3. What about 4a over k? Maybe we'll need one in between, so I'll save a spot. Can you see the pattern here? What's h of t going to be? It's b over k times 1 minus e to the minus 4 now, right? Which is what? 982. 0.982 b over k. So I'm 98% of the way to steady state after 4 a over k's. Okay, and so 98% of the way in this picture, you make the dot big enough, right? You're pretty much there. Okay, and so, we could calibrate one in between if we want. Somebody want to give us 2a over k? So it's going to be b over k times 1 minus e to the minus 2, right? And you said it's what? 0.865 b over k? Okay, so I'm 86% of the way. So, this would be like 3/4 and a little bit more. So right about here. Okay, so you can see what's happening. All right, this thing is filling up, all right? And then I'm at the asymptote there by about 4 time constants. Okay, so this is again why a over k is what we call the time constant of the problem. Okay. Questions? What if I said in the final exam, what are the units of k? Yeah, but does it have units or no? How fast it's coming out? So is it cubic meters per second? Does it? Q out is cubic meters per second. So K would be what? Does H have units? H is length, right? This is length cubed per second. So to get K, I would take meters cubed per second, divide by meters, and I'd get square meter per second. Well, look up here. Square meter per second divided by A. What's the units of A? Square meter. So now I got just per second times time. What's the unit of time? Seconds. Seconds divided by seconds is what? Constant? It's dimensionless. What's e to the 3 feet? How does that compare to e to the 4 miles per hour? I can't have units inside the argument of an exponential function, period. Right? What's the sine of 35 yards? Right? Sine is of theta. Theta is radians. Radians is dimensionless. Right? So there's all kinds of functions that I can't have units inside the argument. It's another thing to be thinking about when you do your math. You can check your answers, right? I can't have e to a length. It's not a physical concept that works, right? I can have length squared, length cubed. I can't have e to length. Make sense? Okay. So, point is, this business has to be dimensionless, right? You can use that to back out units, to check your units. All right, we're beating this problem to death. This is fun, actually. Okay, so how does this relate to the lab? Okay, because in the lab, you didn't start with an empty bucket, right? So, this is the solution that we just did for filling up the bucket. Okay, and so the question now is, how does this problem change if I'm doing the lab? So in the lab, to remind you, okay, all right, here's the governing equation. What was your Q in the lab? Just to remind you of what you actually did, okay, in case you forget what you did in the lab. All right, didn't you start right here, right, with a full container? And then didn't you just have Q out? And then you just plotted this thing. Okay, so in our model over here, this is the most general model, right? A dH dt plus K H of t equals Q plus initial conditions. What's the Q? Qn is 0. I don't have a faucet in the lab. Okay, that makes life a lot easier right away. Okay, and what's the other difference? Initial condition, right? So the initial condition is H of 0 is equal to what? I don't know, but I mean, whatever you started it at, let's call it C. Okay, it's however deep the water was in your container. So in this case, C is not an unknown constant. It's actually the initial height, right? Unknown constants, when we use a C, we'll use like a C1, C2, et cetera. Okay, so C is a known parameter. So now what's the difference? My problem becomes A dH dt, right, plus K H of t is equal to 0, because Qn is 0, and H of 0 equals C. This is now the complete description of the lab problem. So clearly the solution to that's not going to look like this. This is a tank that starts empty and fills up. This is going to be one that starts full and ends up empty. So you can kind of imagine what the answer will look like. But what about the math for solving this whole problem now? It's the same. Is a transient solution for this problem any different than the transient solution for the other problem? First step in the transient solution is to do what? Set the right side equal to 0. Well, first of all, the right side already is 0 in this problem. But in the other problem, when I had Qn equals B, I got rid of that, and I had this. So the transient solution is the same. All right, so H transient of t is going to be C1 e to the minus K over A times time. And so I still have that. And what about the steady state solution? What's the form of my Q in? It's 0, right? So my f of t equals 0. I'm not forcing this problem. I'm not turning on the faucet. Right? When in doubt, if you're trying to struggle with what does that mean for the math, connect it back to the physics. The steady state solution is where this thing ends up. If I don't have a faucet on, where's this going to end up?
0.
Empty, right? If f of t is 0, always the solution h steady state of t is 0. I got a transient part that goes away. I don't do anything in the steady state. I end up with nothing. Okay, so this is great. You hope this is on the final exam. Okay, that's happened before. This is worth 5 points, right, if that happens. Okay, don't know if it'll happen or not. So number 3 is total solution is now the same as just the transient, right? Because there's no steady state. So I get h of t is equal to c1 e to the minus k over a times time. Okay, that's it. There's no steady state. And so what does that mean? Yeah, I need the initial condition, right? So initial condition, h of 0. What happens when I plug in a 0? C1, right, times e to the 0. And that is supposed to be equal to the initial height of the tank, right? Initial height of the water, which is C. So what's C1? Yeah. So that means the C1 is the C. C1 equals C. Okay? So, boy, the lab problem, pretty simple problem, right? And in fact, we can plot some data points with the same table right here, right? Because now my total solution, h of t, is just c e to the minus k over a times time. So help me out. What do I want to use for tick marks? Same thing, right? Same kind of tick mark. So we'll put it right here, right next to it. So this is the h of t. This is going to be the t right here. And we're going to do a over k's. A over k, 2a over k, 3a over k, 4a over k. Okay, and what about the y-axis for h? Say what? C is the starting point, right? So to get a good picture here, yeah, let's put C all the way up here. The initial condition is always the dot on the y-axis, right? So here's where I am. H at time t equals 0 is right there at C. And so in order to get the answer, I want to figure out at various time constants, you know, what this is. So help me out. When I plug in a over k, this is C times what? E to the minus 1, right? Help me out, guys. Calculator. 0.368 times C, right? So at a over k, this is 0.368 C. Okay, and so, boy, what's 1 minus that? Yeah. It's the one from the other problem. It's 0.632. Right? It's the beauty of decaying problems. When the time constant is done in terms of the problem parameters, the answer, the numbers look the same for any piece of physics that you're talking about. Right? Interesting. All right, so great. So for a over k, it's 0.368. So instead of 2/3 of the way up, you know, it's like 2/3 of the way down. Right here. So this value is 0.368 C. Okay, and then let's just do the 4a over k. This is c e to the minus 4. Be 1 minus the other number, but somebody run that. E to the minus 4 is what? 0.018, right, times c. So less than 2% of c. So this is c, less than 2% of it, right? The dot is pretty much kissing the axis. Okay, and you can get a value in between, but this thing just goes like this. Okay, and so that is a exponential decay. Okay, and that's the lab. Okay, so you notice problems that don't have a forcing function tend to be pretty straightforward if they're first order, for sure. Really straightforward. Bam, that's it, you're done. Decaying exponential. By the way, what's the difference, do you think, between this and now I got a problem where I've got, say, a capacitor fully charged, and then I flip the switch and let it drain out? It's the exact same thing, right? I don't have water going through a valve. I have electrons going through a wire. Exactly the same. Okay, so all of these problems that have governing equation like this, they behave the same way. Decaying exponential, or you just change the initial conditions, right? Or the forcing function constant, and you flip that exponential around, or you can shift it up and down on the axis. Right? So all these possible infinite types of problems we could ask you to do for a first order diffie-q, it's some type of decaying exponential in general, moved around the axes in some way, or flipped upside down in some way. Okay, but the procedure is all the same. Does that make sense? Right. Moving on to mechanical systems, which we got to start today and finish next time. Okay, and this one we're going to talk about spring mass systems, which is pretty simple piece of physics to look at, but it's got a lot of richness in the math. So let's see if we can figure out what would we want to do with a spring mass. So I'm going to call this spring mass vibration. Okay, and so the neat thing about this, okay, are you ready for this? This is differential equations in mechanical systems. This is from dynamics, ME 2210. Okay, it's from biomechanics, BME 3212. It's from mechanical design, ME 4140. It's from mechanical vibrations, ME 4210. Okay, so literally what we're going to talk about in the next lecture and a half here is stuff that you will be doing in the senior level classes. Okay? And we decided like this was a good time to just do it right now, freshman year. Okay, so the beauty of it is you're going to see this again, right? You're going to see it again later. And honestly, the math isn't that complicated, right? But now we've got a mathematical model that starts explaining some kind of complicated physics. And this is why we need math in engineering. The physics is too hard to look at it and go, yeah, I know what that's going to do. Right? The idea that, I can build a bridge and design the whole bridge to withstand, all of this traffic on it and everything else. But all of a sudden the wind blows at a certain rate and the bridge just starts oscillating out of control, right, and crumbles. All right, that happened to the Tacoma Narrows Bridge. Right? And in aircraft structures, right? If you don't design this thing right and the wind blows the wrong way or the turn comes the wrong way, then all of a sudden your wing starts doing this out of control until it breaks off. Not good, right? So complicated phenomena that is not obvious just by looking at it. I've got to have mathematical models to figure out what happens to things when they're oscillating and vibrating, and what are the things to avoid when I'm designing them so I don't kill people. Okay, important. All right, so all of this from a spring mass vibration. Okay, so here's a problem I want to look at. And I brought a spring and mass, and you guys are doing this in lab, I guess, this week right now. Okay, but here's the problem parameters we'll be looking at. Okay, I've got a mass, M, and I've got a spring constant, K, right here. Okay, and what I would like to do, okay, is I would like to displace this thing, okay, and track the position y of t. But here's an argument. I'm going to measure this from the equilibrium position, okay, and I'm going to motivate why that is here in just a minute. Okay, so we'll measure that from the equilibrium position. Okay, so what I mean by that is, here's a spring. It's got a certain length to it, undeformed, okay? If I put a mass on a spring, independent of it being a dynamics problem, and I just statically let it stretch the spring out. Clearly this spring, right, statics problem, the spring, it's not oscillating now, but the spring's a heck of a lot longer than it used to be, right? And so now, if I call this 0 and displace it and let it go, it will oscillate about the equilibrium position, okay? That is a different mathematical description, okay, than if I do this. Here's the undeformed length of the spring, and at t equals 0, I just let it go, right? Because I have initial energy dumped into it because it free falls for a little bit, right? I mean, so if I start with equilibrium, that means the spring is balancing the weight, right? And if I come and displace it from equilibrium, that becomes the midpoint now, right? It just oscillates above and below that, okay? So essentially the whole problem ends up just shifted if I start here, right? And then bam, now it's oscillating below, so the whole thing's just shifted. Okay, so mathematically that's a little more, it's an extra step to deal with, and so it makes more sense to tackle this problem just by readjusting the 0 point. Okay, so we're gonna define y equals 0 to be right here at equilibrium, and we're gonna consider what happens like this. Okay, so a couple things to think about. Okay, number one, what's a governing equation for that? Okay, so let's think about, what are the forces and things involved. Now, reminding you in this class, we're not going to be asking you to derive any governing equations on exams, right? So this is just really for your entertainment, okay? How do we come up with the equation? So I'd like to consider it two different situations. Okay, one is we will look at a free body diagram, right? A free body diagram, we talked about this before when we did statics, right? So this is a free body diagram, we'll say at equilibrium. Okay, so at the equilibrium position, which is y equals 0. Okay, and so what's it going to look like when this thing is not a dynamics problem, okay, and it is just right here. The spring is elongated, and the mass is sitting there, and it's in static equilibrium. What are the forces that are acting on that mass? All right, gravity. Is gravity a force? Yeah. So just to be clear again, we are in the vertical plane, so I got g here. So gravity is an acceleration, so how do I get force? Mass times acceleration. So I know I've got this, mg. That's the weight, right? Weight is force. Gravity isn't force. The weight is mg. Okay, and is there any other force acting on this thing? Yeah, I mean the spring's what's holding it up, right? If it was just that, it would be free falling. Right, so it's not free falling, the spring's holding it up. Okay, and so how do you get the force in a spring? There's tension in it, but what was that? K times x. Okay, so in this case, what's x? The displacement from equilibrium, getting warm. Okay, so here's the original length of the spring, undeformed, right? Now I let it stretch statically, and it's here. So the spring's longer, right? So the spring has been stretched by some amount, say delta, right? Or x, okay? We'll call it delta. So what's the force in the spring then? Kx plus delta? Just to be clear, I'm calling the x delta, right? Delta minus kx. All right, so here we go again. Undeformed. Now it's deformed in amount delta. And the delta is just enough to hold it up, right? So what's the force in the spring? Delta what? K. Yeah, delta times k, right? K times delta. Spring force is just k times the deformation, right? So I got k delta in the spring. So k times, I'm going to use that, Greek letter delta. So delta is what we're going to call the equilibrium elongation. Right? So this is how long I have to stretch the spring in order to make it in equilibrium. All right, great. So that's it in equilibrium. Now, let me ask you this. The problem we want to solve is if I displace it from equilibrium and let it go. Right? This problem. So, the question now is at any point in time, what's going on with that? So we should probably think about what are the forces during the dynamics problem now, right? So this is at the equilibrium, statics. Now let's look at the dynamics. So this is step number 2. Let's look at the free body diagram, okay, for y of t greater than 0. Okay, so we want to think about this. This would also mean that time is greater than 0. Okay, so this thing is later on somewhere. So let's think about this. If I'm initially here, okay, and this is the starting point. Now I'm going to move to where the middle of the box, okay, is some distance down now, y of t. Okay, so I'm going to go ahead and draw the forces. Here's equilibrium. The picture I drew is down relative to equilibrium, right? It's gone down past there. How could we write the forces that act on the mass now? Do I still have the weight? Sure. All right, gravity is still gravity, so I've got a force of weight, mg. So the question really now is, what's this force right here? Okay. And just remember, the force in a spring is just K times however much you stretch the spring. So before it displaces at all, the spring is stretched, right? By an amount delta. Now, I add a y of t to the delta. What's the total elongation?
K delta plus y of t.
Yeah, so the total elongation is now delta plus the y of t. So the force is just k times that, right? Okay, so at this point in time, what we're going to have is a k times the sum, right? This force right here will be k times the sum, delta plus y of t, like that. All right, very good. So, what's the difference between these two cases? When I add up these forces, what should I get? 0. This is equilibrium. When I add up these forces, should I get 0? What should I get?
More than 0.
More than 0? Okay. Do I know what it has to be equal to based on some, law of physics? Has to be what? When something's not in equilibrium and I add up the forces, what do I get? MA. Again, if you haven't had physics, but we have brought this up several times in this class, right? That when you add up the forces and you don't get 0, it means you have dynamics, right? And dynamics means the forces has to add up to mass times acceleration. Okay? So let's think about that. Let's do this one at a time here. Over here, equilibrium, the sum of the forces has to give me 0. So take a look at the forces. K delta is a force up, right? Minus a force down, mg, has to equal the total. So can I find delta? What's delta going to be? Yeah, it's the weight divided by the spring constant, right? mg divided by k. So first of all, delta, I know what it is, right? The original problem parameters here, delta is just mg divided by k. Great. That's what I get from statics. Over here, when I add up the forces, sum of the forces is supposed to equal what? ma. Can I, what about a? Is a constant? Here, take a look at the problem. Acceleration constant in this problem? Probably not, right? It's changing direction. Okay, so I mean, even the force seems to be, the acceleration, it's going up, then it's going down. There's something going on here. Okay, so the acceleration is not a constant, so I probably shouldn't just call it a. What's y of t? It's displacement, it's position, right? How's acceleration related to position? All right, so it's meters per second squared, but what? It's the second derivative, right? So when I add up these forces, shouldn't I get m times 2 derivatives of y? And I'm going to call that y double dot, right? Y double dot of t. Again, the double dot means 2 derivatives of y with respect to time. So that's the difference. This one, sum of the force is 0. This one, sum of the forces is my double dot. So clearly, I'm going to have derivatives in the equation here, right? All right, so let's add them. What are the forces? Sum of the forces are, what do you think? By the way, is a positive y down or up according to this drawing? Down. So let's stick with the sign convention that we have in the picture. So we'll write mg is a positive force down minus the force up, which is k, times delta plus y of t. Right? That's the forces added up. And that should be equal to this guy, right? m y double dot of t. Right? Wouldn't that be the sum of the forces equals ma? So what does that tell me? Let's plug it in and find out, right? So I got mg minus k. Do I know what delta is? Yeah, statics told me what delta is. Might as well plug it in. Mg over k, right? Mg divided by k is delta, okay, plus y of t, right? All that's multiplied by k, all right? And this is supposed to be equal to m y double dot. Well, that's interesting. Look what you get here. Mg, what's k times mg over k? It's mg again. Interesting. Okay? Minus ky of t is equal to m y double dot. So the weight, the force of the weight, does that affect the dynamics? Nope. Okay, now you need to be careful. Is the dynamics the same if I change the mass? Right? I mean, when you look at that, you say, hey, the weight cancels out. So, I mean, I got this weight on there. Right? Take a look at the dynamics here. Here's the weight. I can change the mass and see, right? Here's another one. Let's put another one on here. See what we get. Okay, clearly it changes the starting point, right? Does this dynamics look like the last dynamics? What's the difference? Deeper, okay. Greater magnitude of oscillation. Is the magnitude really the difference here? It's slower, right? It's the speed of the oscillation. It's the frequency of the oscillation seems to be different. So it's not that the mass doesn't matter, but the force of the weight does not change the governing equation because the force of the weight cancels out. Okay? That's because we defined the thing, right? The weight is not in the equation because we defined equilibrium to be at the elongation. Right? So the equilibrium elongation is the starting point. We took care of the weight by doing that. Okay? And that's the reason it cancels out. Okay? So this is 0. right? And so what's the net result? If I put all this on one side of an equation, I get my double dot plus k y of t is equal to 0. Okay, now, this is a second order equation. I'm going to put plus initial conditions. We'll have to talk about what those are. Okay, and so what we have here is a second order, right, linear differential equation, okay, with constant coefficients, which means the recipe will apply. All right, so let's think back about this again. I mean, why do I care? All right, why do I care what the solution to this thing is? Okay, I talked about things like the airplane wing breaking off while we're flying the plane. That would be disturbing. Okay, but let's think about this. I mean, is it obvious to us what the answer is? Okay, if we don't solve this equation. So, for example, you guys commented that this thing seems to be oscillating faster than if I put two masses on. Okay, so what would common sense say? All right, in fact, let's just look at it real quick. So here it is. All right, one mass. Take a look at it. Get a feel for how fast it's going. Okay, and let's put the second mass on. And it kind of stands to reason. Clearly the equilibrium elongation is twice as much now, twice the weight on there. Okay, and when it oscillates, well, I got twice the mass. I don't know, is it going twice as slow? Maybe, right? I mean, we could measure that, right? Two masses, twice the elongation, seems to be going twice as slow. Let's see if it's going twice as slow. So somebody here who can time me for 10 seconds, we can do this a lot better than the 1 meter drop. Okay, so 10 seconds, I want us to count how many cycles we get in 10 seconds. Who can tell me to start on this? We'll just count out loud when we're. Yes. Give me a 3, 2, 1.
3, 2, 1.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
Stop.
All right, so I got 10 cycles in 10 seconds, right? It's almost like I bent the crap out of the spring till I could get it to be 1 hertz. Okay, that's exactly what I did, right? So it's 1 cycle per second is what this is. Okay, great. So twice as slow is what it kind of looked like to us. I mean, let's put 2 on, and let's do this experiment again, all right? And see, it's clearly it's stretched twice as much. It's twice the mass. Okay, so you give me the 3, 2, 1.
3, 2, 1, go.
1, 2, 3, 4, 5, 6, 7. What's half of 10? It's not 7? Damn. Okay, so we better solve a differential equation, right? Figure out what's going on. So we will pick up there next time.